Okay, so we were considering logistic map. We studied logistic map. Un plus 1 equals to f of un, where f of u is ru times 1 minus u defined on the domain 0, 1, and parameter r can have values from 0 to 4. We know that for some values of r, we have stable periodic solutions. For some values of r, we have stable solutions, stable periodic. Or fixed solutions. And this means that un converges to this solution. However, for some other values of r, there are values of r when there are no stable solutions. And that these values of r we have chaotic solutions. These solutions appear for two reasons. First is stretching. And second is folding. Now I will explain it. What does it mean? So in logistic map, if say u node belongs to 0 half, then u1 belongs to 0, 1. So this is stretching. Also, if u node belongs to half 1, then u1 again belongs to 0, 1. Again stretching. Let's put it like this. 0 half so mapped into 0, 1, half 1 also mapped to 0, 1. So these are stretching. This is stretching. And this is also stretching. What is interesting, so they both, this subdomain and this subdomain, they are stretched into the same segment 0, 1. And this is called folding. So what we can say? We can say that chaos occurs when map is stretching and folding. Okay, now look at folding part. Folding means that f of u is not one-to-one function. So f of u is not invertible. And this is called Arnold's conjecture. So it sounds like this: no chaos if f of u is invertible. The second part of the story is also interesting: stretching. Stretching is mathematically described by so-called Lyapunov exponent. So to introduce this Lyapunov exponent, let's consider two orbits. So one is starts with x at x0, x1 and so on, xn and so on. And for second starting point is y0. Assume that these two orbits start very close to each other. So what it means? It means that y0 equals to x0 plus epsilon naught, where epsilon naught by absolute value is much smaller than 1. Now let's see what happens. So epsilon naught gives distance between y0 and x0. let us find the distance between yn and xn. So this will be epsilon n equals to yn minus xn, and this would be equal to n composite map of y naught minus n composite map of x naught. And we can put it like fn of x naught plus epsilon minus fn of x naught. And if we use, by using first order approximation, we can put it like fn at x naught plus dfn over dx at x naught times epsilon naught. So this is this, and minus fn of x naught. So this and this term cancel, and we get the derivative of n composite map over x when x equals to x naught. So let's consider, so distance would be given by absolute value of epsilon n, and this will be equal to, sorry, yeah, I forgot times epsilon, dfn over dx at x naught by absolute value times epsilon by epsilon. So let's introduce lambda n. It is in fact sequence of numbers such that derivative, absolute value of derivative of n's integrate of map f over dx at x naught by absolute value equals to e to the power of lambda n times n. Or from here we get lambda n equals to 1 over n times logarithm of dfn over dx naught. So let's consider, so this is lambda and this is sequence. Let's consider limit of this sequence. Lambda, which equals to limit when n tends to infinity, 1 over n times logarithm of absolute value of this derivative. And this lambda would call Lyapunov exponent. Lambda is Lyapunov exponent. Why we can introduce it and what does it mean? So we consider dfn over dx naught, this sequence. df tx naught df, say 1, 2 of tx naught, so on, df n over tx naught, and so on. If this sequence increases or decreases exponentially, then lambda is finite number. If this sequence slower than exponent, so it increases or decreases, but not exponentially, but slower, then lambda is 0. And if this sequence is faster, lambda is infinite. So this is what it means. So what in terms of stretching, what it means? If lambda positive, we have stretching. Epsilon n tends to infinity. If lambda is less than 0, we don't have stretching. Epsilon n tends to 0. So what it means? Here we say 2 orbits diverge, and here 2 orbits converge. So if 2 orbits diverge, we have stretching. If 2 orbits converge, we don't have stretching. Now let's consider df n over dx naught. So we remember what is it? It was derivative of f at point x n minus 1. We derived it earlier. Derivative times derivative of x of f at point x n minus 2 times so on, and up to derivative of f at x naught. And therefore, logarithm of df n over dx naught will be equal to logarithm of absolute value of f prime at x n minus 1 times f prime at x n minus 2 times so on times f prime at x naught by absolute value. And this logarithm of product equals to sum of logarithms. This will be equal to logarithm of f absolute value of prime at x n minus 1 plus logarithm of derivative of f at x n minus 2 by absolute value plus so on plus logarithm of the absolute value of derivative of f at x naught. Or we can put it like sum of logarithms f prime xi, I changes from 1 in fact to n minus. And now if we get back to Lyapunov exponent therefore equals to limit when n tends to infinity of 1 over n of sum logarithm of absolute value of prime at xi, where I changes from 0. We can put here n minus 1, but we can also put n because one term is not going to change. To change this here can be also so this is definition of Lyapunov exponent. So this is which you're supposed to remember. Formula to remember. So this formula in fact means that lambda is average value of logarithm of derivative of f along orbit. And now we can consider examples. So first example. Assume f prime of x is constant for the map. Then, for example, like E W. What I can put here, for example, xn plus 1 equals to a times xn mod 1. Then f prime of x equals to a for any x. So in this case, lambda is equal to logarithm of f prime. And if f prime of x by absolute value less than 1, then lambda is negative and we don't have counts. Alternatively, if derivative of f absolute value is more than 1, so we have counts. Counts, it's again so provided that solution is bounded. So we should have folding also. If solution is bounded. So this is one example. Second example, another example. Assume solution is converging to stable fixed point. Well, if it's convergent, fixed point should be stable. Then f prime of x tends to f prime at fixed point. X capital is fixed point. And therefore lambda tends to logarithm of absolute value of prime of x capital. And if, since x capital is stable, f prime at x capital absolute value is less than 1, and therefore lambda negative. We don't have stretching. And last example. So consider the case when solution converges to periodic solution. Solution which is stable, otherwise it would not converge. So in this case, f prime at ui, so along the orbit, ui tends to, say, f prime at, we have x1 if I equals to 2n plus 1 and f prime of xi tends to f prime of x2 capital if I equals to 2n, and here x1, x2 is stable periodic solution. So what it means? It means now that lambda, which equals to limit when n tends to infinity of 1 over n times sum of logarithm of f prime xi, I changes from 1, say, to n. This can be shown as it will be equal to 1 over n times half of logarithm of f prime at x1 plus logarithm of f prime of x2. Which is half of logarithm of product f prime at x1 times f prime at x2. And we know that this by absolute value should be less than 1 because we have stable to periodic solution. For stable to periodic solution, this product should be less than 1, and therefore this will be negative. And again, we don't have stretching. No stretching.